simple date-filtered query scanned 2 terabytes and took 30 seconds. The culprit? No clustering key on the orders table, so micro-partitions couldn't be pruned. Let's explore. We'll master 3 powerful techniques: clustering keys, search optimization, and query profiling. You'll learn when to use each, how to implement them, and how to avoid common pitfalls. By the end, you'll be able to reduce query costs by 50% or more. When a query comes from your browser, Snowflake's Query Optimization reduces the amount of data scanned per query. This lowers costs and improves response times. The compute layer applies 3 techniques: clustering keys, search optimization, and profiling, all focused on optimizing storage. Snowflake stores data in compressed micro-partitions, typically 50 to 500 MB each, with metadata like min and max values. When a query filters on a column, Snowflake uses this metadata to skip partitions that don't contain relevant data. This is partition pruning. But if data is inserted randomly, ranges overlap, reducing pruning effectiveness. Clustering keys reorder data to minimize overlap. Use the system function system $clustering information to check clustering depth and overlap. A high average depth means poor clustering. Monitor this regularly. Start with columns your query filters on in where clauses, high cardinality like order date, not low cardinality like status. Define the clustering key with alter table cluster, by so Snowflake prunes micro-partitions. After defining the key, you can manually recluster to reorder existing data. Then use system $clustering information to check the clustering depth. It should be close to 1 for optimal pruning. Clustering on a low cardinality column like status creates wide partitions that defeat pruning. Switching to a high cardinality column such as ordered enables precise partition pruning, making clustering effective. For any query, search optimization creates a search access path that works across micro-partitions, enabling fast lookup for selective queries, like where email equals user at example. Even if that column isn't clustered. It does use extra storage and credits to maintain. Enable search optimization on the whole table or specific columns. Use show tables to verify it's active. The initial build can take hours for large tables. Enabling search optimization on every column, as in the before code, burns credits unnecessarily. The fix limits it to columns used in selective queries like email and username, reducing cost. Explain shows the query plan, including how many partitions are scanned. If partitions assigned is close to partitions total, pruning is poor. Also check for spills, which indicate memory pressure. Use query history for historical data on spills and overall performance. Use explain to see partition pruning stats. Then query history to find slow queries and analyze their scan patterns. Snowsight's Profile tab visualizes the query plan with timing and spill information, which helps identify full scans and inefficient joins. Look for operators with high execution time or spilled bytes. Then fix the issue by, for example, increasing warehouse size to reduce spills. Get the query ID from history, then open the profile in Snowsight. You can also call Snowflake Information Schema Query operators via table for detailed operator statistics. When you issue a query, clustering and search optimization complement each other, both operating on micro-partitions. You can use both on the same table, cluster by date for range scans, and add search optimization on customerid for point lookups. Then the optimizer picks the best access method as the result. Create a table clustered by order date and add search optimization on customerid. The query uses both. Search optimization finds relevant partitions, and clustering scans only those. The root cause: the orders table had no clustering key and data was inserted randomly. Micro-partitions had overlapping date ranges, so no pruning occurred. Every partition was scanned, scanning 2 TB. The fix was to add a clustering key on order date and recluster. Now micro-partitions have narrow, non-overlapping ranges, enabling effective pruning. The query only scans partitions containing the target date. Success! This prevents future full scans. Automatic reclustering may not keep up with large inserts, leaving the table poorly clustered. Manually run alter table mytable recluster to reset clustering depth and restore scan efficiency. Use these commands to diagnose issues. Check clustering depth using system $clustering information, explain queries to see pruning, and monitor query history for large scans. Set up alerts for queries scanning too many bytes. Time for interview questions. A clustering key improves partition pruning. Automatic reclustering runs continuously while manual gives control. To troubleshoot, use explain and check clustering depth. FAQs demystified. Clustering reorders data for range scans. Search optimization creates an index for point lookups. Use clustering when depth is high or pruning is poor. They work together. To recap, clustering keys improve pruning for range scans, search optimization speeds up point lookups, and profiling helps identify bottlenecks. Combine them for optimal performance and monitor costs regularly. Thanks for watching. The full article and code examples are covered in detail at thecodeforge.io.